My name's Ruben. I sort of play around with some driver coding occasionally. This is the setup that I have. I do all the coding on my laptop and then transfer it to a Raspberry Pi 4. There's a little breadboard there, and on there's an LED button switch. And with that, I can experiment doing GPIO drivers in Linux. So a little bit about me. I'm a retired electronics engineer. I sort of went from chip design in the 1980s and 90s to helping out customers in Europe debug circuit boards, mainly in data communications. Often I ended up, as well as debugging the electronics, I ended up getting into debugging drivers because often the drivers were setting registers and things incorrectly. So the electronics on the board wasn't working properly. So from sort of bottom up in hardware, I sort of got into drivers. Initially just debugging bits of code. And then I sort of got an itch how to learn how to write drivers. And with that, I bought a Raspberry Pi and sort of started teaching myself with stuff that's online. So the role of a Linux driver essentially is to allow applications to access hardware. The Linux drivers, they live in the kernel. They can be controlled by applications. Applications use system commands like read, write, open, close, as if the hardware was a file. So this is the old Unix, everything is a file philosophy. And the thing with drivers is because they are in the kernel, it means they've got all the same permissions as the rest of the kernel code. So if you're writing a driver, if you get into this, you've got to be quite careful because you've got access to all the memory and all the hardware. So you have to take some care not to break anything, basically. Normally with applications, when they're in user space, they tend to be sandboxed. They can't do that much damage. If they crash, they crash and the system can recover quite quickly. But if you crash a driver, it depends what you're controlling, but you can cause some damage. As I said, applications, they can read and write device drivers. The other way that device drivers sort of get activated is from the hardware itself, when the hardware sends interrupts to the system. So it's device drivers that deal with interrupts. So if a piece of hardware needs some attention, it'll send an interrupt, and then the relevant device driver will have to do something about it. In Linux, there's two types of drivers. That are ones you can load dynamically. Those are called loadable kernel modules, or LKMs. And then there's the ones that come with the base kernel. They're already built in. Normally, you have quite a initial image for a base kernel is relatively small with a few built-in drivers just to get the system started. And then as you boot up and you detect other piece of hardware, then the boot up process will start loading other kernel modules depending on the hardware that's detected in your system. The other good thing about loadable kernel modules is that you can write your own modules and then just load them when you want to. And that's what I do with the GPIO drivers. The other advantage of using loadable kernel modules is that because you can dynamically load them, you don't have to recompile the whole kernel each time when you write a driver. You just write your driver, compile it, and load it. See if it works, and if it doesn't, unload it. The kernel modules, they all come with an extension .ko, standing for kernel object file. They typically live up in lib/modules/ whatever your kernel version is. Linux traditionally has sort of three driver types. There's the simplest type, you might say, is the character driver. This is where you send data to and from a device in streams of bytes. Then there's There are block drivers for disk drives, multimedia storage devices. These can get really complicated from having to sort of support different file systems. And probably the most complex sort of drivers are network drivers. The character devices and block devices, applications interface to them through what's called device files. And the device files, they live in your /dev directory. Network drivers, on the other hand, they don't really have device files. They have sockets. Sockets are kind of opened in a similar way to device files. So in device files, we have file descriptors that are used to reference a file, just like a normal file in Linux. With sockets, you have a thing called socket descriptors. But we're going to focus on character device drivers, because that's what we're going to use for accessing the GPIO pins on a Raspberry Pi. The device files, as I said, you can see those in the /dev directory. If you go in there and you list them, you'll see a whole bunch of files beginning with C. Those are character drivers or child drivers. The ones beginning with B are block drivers. So there, for example, an I2C device, I2C device, that's a character driver that's being used there. Block devices here, so these are multimedia. This will be some sort of SD card that's on my Raspberry Pi. The drivers themselves, you might give them a name, but the kernel only recognizes them by numbers. So every driver will have what's called a major number. So in this case here, for the character driver controlling these I2C ports, the major number is 89. And that driver controls 2 ports. Those are referenced with a minor number, so 20 and 21. Likewise, with the block drivers, you've got the overall sort of hard drive itself, or SD card, is referenced with major number 179. That's the driver for it. There's a couple of partitions on there, and they're referenced with minor numbers 1 and 2. So that way, when you're writing, an application is writing to any of these device files, and it will write to these device files as if it were a normal file. So it will use open, write, read, close. It'll, as soon as you write to one of those device files, Linux will know what driver to call up. It'll know that if you write to, I'll show you what the device file is in a minute, but at the moment, these are just the numbers here. There isn't the actual names of the device files here. Sorry, there is. Let's go to the next one. Let me do an example with a TTY. So if you type the command TTY, that'll call up the device file that's currently being used for your TTY. In other words, it could be like your Linux terminal. So if you're running a Linux terminal in the GUI, in this case, it's /dev/pts/0. So PTS stands for sudo teletype slave. Now, if we list that, it'll give us some information about it. So this device file here, it's got a major number of 136 and a minor of 0. So the driver is referenced by number 136 by the kernel. So whenever we want to print to this device file, Linux knows that it has to call up driver number 136. And that will then cause whatever you're printing to go to your terminal that's in your GUI. We can, if we look in a directory called proc/tty/drivers, we can find out the name of that driver that relates to that. There's the major number, 136. And the driver is called PTY slave. So this is the driver that's responsible then for any program that you're running in a terminal here. It's printing something to the screen. It's going to use this driver called PTY slave to print it. So as an example here, let's say we want to print hello world. So it could be a Python program, it could be a C program. When it prints, it's going to print to what's called standard output in Linux. In my system here on the Raspberry Pi, standard out is connected to this slave pseudo terminal with major number 136. What will happen is any output that gets printed to this file, it's a pseudo file. It's not a real file, but it's just a file that sort of pretends to be a file. The kernel sort of gets triggered every time it sees something going to that file, and knows then it's got to call this slave driver here. When that slave driver is called, then we print hello world to the screen. Let's have a look a little bit under the hood of that printf statement. Printf calls printf function from the GNU C library. That hello world could have been printed by a Python statement as well. Python also uses the GNU C library. In fact, a lot of high-level languages in Linux will be using the C library. That print statement, in turn, when you go under the hood of that, eventually calls a write call. And that write call, it's just a system. It's really just a wrapper around a system call called syswrite. At this point, we're into sort of machine-dependent code. So if you're running Linux on an Intel machine or Linux on an ARM machine, the assembly that's in that system call here will be different. On the Raspberry Pi, that's ARM based. So when it sees that we want to do a system write, we're going to load the number 4 into a CPU register. And then switch the CPU to kernel mode. In kernel mode, the CPU sees that a 4 has come down there to its lookup table. And it knows that's a system write command. And then through a number of layers, it will send that system write command to that driver. That driver knows that it's a write command. And it's got to write something to the screen and then print hello world. So all our child drivers that we write, they interface in this sort of way. So any application will use a system call table to write to the driver or read from the driver. So we need to get started in driver writing. You need some very basic tools. You don't need very much. The main thing you need is the kernel header package, which is kind of to kernel drivers what the C library is to applications. So it defines interfaces between the driver and kernel components, and also between the kernel and user space. Normally, it's not installed with your Linux distribution. You tend to have to install it separately. For the Raspberry Pi, the best thing, every couple of years, the way you install it, it changes a little bit. So when you want to install the header package, the best thing is to go to the Raspberry Pi documentation and head to the Linux kernel documentation. There's always a section in there on how to install the latest headers for the latest Raspberry Linux system. Now, let's have a look at a very simple driver module. So At the top of the module, we have the headers that we were talking about before. These are the kernel headers that we have to include. Every module always has an initialization function. That runs as soon as you load the module into the kernel. It initializes, typically it'll initialize hardware, and it also register with the kernel what this driver can do. Anyway, this is a very simple hello world type module. The reason it's a good, if you get into this, it's always a good idea to start off with a very simple hello world module, because when you try and compile this, it'll test whether you've installed your headers properly, the kernel headers, and just got your sort of development environment set up correctly. Then the other thing the module has is an exit function. So when you unload the driver, this is what runs. And typically with drivers, you use this to put any hardware you're controlling in a stable state. So if you've set any output pins accidentally, you want to make sure all the output pins on your device are not floating. So a number of the GPIO pins, they can be high or low or tri-state. You don't always want them to be leaving them in a tri-state mode is not really a good idea. There's nothing connected to them. So, and the other thing you do when you're exiting is any resources you've used from the kernel, like memory, IR, interrupt request numbers, and so on, you just hand all those back, you release all those. These in and exit functions you have to register so that the kernel knows about them when you load the driver. And then the last thing at the bottom there is typically you put a module license statement, an open source license like GPL. The reason for doing that is if you don't put that in, you try and compile this, it'll compile, but you'll get error warnings saying that you've tainted the kernel. So, the most basic statement in the driver is probably print K. So this is the kernel sort of print equivalent statement that you might use in user space. You'll be using this a lot for debug purposes. This print K doesn't print to the screen directly, it prints to a kernel buffer, log buffer. And to read that, you need to use the Linux command dmessage. Typically, you print with certain what's called kernel log levels. So I use a log level of kern info. So that's not very high priority. If you think there might be something in your program and something bad happens and you want to print something very high priority, you can use the kern emergency log level. So that'll get printed before other messages get printed. Now we need a makefile to go with that simple hello world example that we had before. Now, the first thing you need to do is specify the directory where your kernel headers basically are sitting, and also where your kernel sources are. So you do that with this statement. There's a variable called KDIR, kernel directory. You give it a path name. It's usually in lib/modules, and like I say, the actual module version name, and then there's a /build directory. Now, if you've installed everything correctly, that's where all your kernel sources will be. Now, when we type make for this makefile, what it's going to do, it's going to sort of do it in two stages. As well as it's going to start off in your local directory where your hello.c file is living, and then it's going to switch to to the kernel source directory, where there's a whole bunch of kernel kbuild files, they're called. And that is so that your kernel module can be linked in with the kernel components that it needs. And that's essentially what this statement does here. So this -c statement says change to the kernel directory and carry on making in there. When it's finished, it'll come back to your directory and eventually create what's called a hello.ko file. So this is the kernel module. Normally, to insert a module into the system, a simple way of doing it is to use the insmod command. I've just put it in the make file here so that I can just type make load. I don't have to keep remembering my module name. When I type make load, it's going to run this insmod command here, and it'll load hello.ko. And I have another helper function. I want to unload the module. I just type make unload, and it'll run rmmod hello. Those are your two basic unload and load commands. This thing I've highlighted here, object minus m equals hello.o, that's basically telling the compiler that I want to create a loadable kernel module. So M here stands for a loadable kernel module, not a built-in module. If I had obj minus y there, object minus y, that would actually create a built-in module, but I don't want that. So the steps are hello.c ends up becoming a hello.o object file. That's the first compilation step that happens with this make file. Then the make process sees this statement here, and then takes that hello.o file and converts it to a hello.ko file, the final kernel module. You'll find that there are going to be loads of files created. Even for the simple hello.o thing, there's probably going to be about 10 files that suddenly appear in your local directory. So you might want to clean them up afterwards. You don't need all those files, so you can just type make clean everything up. So for my GPIO driver test setup, it's pretty easy. Got a breadboard here, an LED, and a push button switch. The idea is when I press this switch, the light should come on. It should trigger, that switch will send an interrupt to a driver running on my Raspberry Pi, and then it should just light the LED up. So the electronics is pretty simple, but the driver starts getting quite complicated. So a typical basic driver has got three big sections to it. We've already talked about one, the initialization and exit sections. They're just triggered by loading and unloading the driver. Then we have a section of code in there which is for transferring data. So writing to the registers, reading from the registers. Those operations are all initiated by the user application. And the other thing we have to put in the driver is how to deal with interrupt requests. This is where it gets tricky because interrupts can occur asynchronously. It can happen anytime. So when an interrupt request happens, some routines in your driver are going to spring into action, and they're all triggered by the hardware. So one thing which is different from drivers to programs running in user space is that drivers are all completely event-driven. Once they're loaded, if the application doesn't do anything and the hardware doesn't do anything, the driver doesn't do anything either. It just sits there. It doesn't run like a program from beginning to end, like programs do in user space. It's basically just a whole sort of pile of Lego brick functions. And then when something happens from user space or from hardware, one of those Lego bricks gets called up and does something. And the whole thing just goes back to sleep. They're talking about data transfer. So in a character device driver, as I mentioned before, the application, for example, if it wants to write to the GPIO registers, it'll issue a write command. That in turn goes to what's called the virtual file system, which Linux has. So Linux has this virtual file system whereby it makes certain drivers like block drivers, character drivers, look like files. And that eventually propagates to your character device driver. And you have to provide functions in there that can deal with these system calls coming from the user application if you're writing one of these character device drivers. So we have an open function, which would be the equivalent to opening a file. In this case, this could be opening and setting certain parameters in the registers for the GPIO device. We have a device write, which is equivalent to writing to a file in user space. In this case, you'll be writing to registers, setting registers up. You may want to read registers, for example, reading the status of a pin to see if it's high or low. Now, when the driver is not being used, you can call the release function. Effectively, what that does, it means that the device file that's in user space can now be used by another application. Well, we've mentioned the virtual file system. This construct, write, open, write, read, release, these are all operations that are defined in a data structure called file operations that you have to put into your driver. I won't, it's typically called a file operation structure. It's one of the most basic data structures that you use in your driver. I won't go into too much detail about it now, but in that you define all the functions that are applicable to your driver. So in this case, open, release, read, and write. There are others you can do as well, but they're usually the most basic ones. And these then get registered with the kernel, and the kernel knows that your driver can support those sort of functions when an application tries to access the device file that's connected to that driver. Right. Next thing we have to do with our GPIO driver is we've got to deal with interrupts. We've got a press button there that we're pushing, which is going to trigger an interrupt. There's a couple of options here. For example, we could have I'm just highlighting that you can have a web application here which writes to a device file. But in terms of interrupt handling, what we can do when we press this button here, that'll send an interrupt request initially to quite a small routine, just called an interrupt service routine. If this was a more complicated piece of hardware, the ISR would actually send an acknowledgement back to that piece of hardware just to let it know, I've received your interrupt, you can turn it off now. Then we need to do something. We can either, the thing that we need to do, for example, switch on the LED, or as this is a switch of some sort, which might have some contact bounce, we might want to filter that contact bounce in software. We can schedule what's called a tasklet. That'll switch the LED on, or toggle the LED if we want to switch it off. And also maybe you can have a little filter in that, a little software filter in there for filtering out the contact bounce. These two functions here, they're all running in what's called interrupt context. That means the CPU stopped whatever else it was doing, and it's just focusing on servicing these routines here. Anything you sort of put in here has to really be very quick to stop wasting CPU time, because basically the CPU is now dedicated to your interrupt request. If what you're doing in this tasklet actually could take a long time, it might not be such a good idea to have it running in interrupt context. It might be better to put this into what's called process context, like so. In that case, you have what's called a primary handler here, which does, again, just the basic stuff, acknowledges interrupts, and then schedule what's called a threaded IRQ handler. This can run now in process context. This means the CPU can decide when to deal with it, essentially. It could sleep there if it wants. If it's not urgent and the CPU's got other better things to do, it'll wait till it actually deals with whatever needs to be done in here, like switch the LED on or off. So these are sort of design decisions you have to make in your driver. One of the things that happens, something like a Raspberry Pi, it's a 4-core processor, the Raspberry Pi 4. So one of the things you've got to be aware of, because we're dealing with a driver, which can be accessed from an application user space as well as from the hardware, it means different threads may be wanting to access the same piece of memory at the same time. So for example, with the GPIO registers, it could be there's an interrupt service routine that may be wanting to access those registers, and accidentally at the same time, while somebody from user space wants to access them as well. And then you get a race condition. And that tends to happen in multi-core processors. You can have two threads, thread A, thread B. They both want to access the same critical code and data area and memory. So we need to prevent that somehow in our driver from happening. So one of the things you can do is use spin locks. So in your driver, for example, the routine that's switching the LED on might be wanting to switch it on. You want to prevent something else from switching the LED off. That thread there can acquire what's called a spin lock. That means if there's another thread which comes along, wants to access the same register, it'll now have to spin. So that's just the CPU spinning around, waiting for thread A to complete. Once thread A is completed, it'll release the lock and give it to thread B. Thread B can then acquire the lock, and it can then do what it wants to do. But at least thread A has done what it needs to do. You're not going to get data in the RAM corrupted. Each thread will be acting in sequence, not at the same time. You don't really have this problem on a uniprocessor machine. This just crops up on multiprocessor cores. As I mentioned before, you can get this when you're pressing a push button. You can get this sort of issue where you get these spurious contact signals. So as you're pressing the button, the contacts, they actually bounce up and down a little bit. And so you get this rising and falling of the pulses before the contacts, before the switch stays high, effectively. Normally, you would debounce the switches in hardware on the board, like with a simple RC filter, for example. Or it might even, if it's a quite an expensive switch, it already have the debouncing circuitry inside. but I've only used a cheap switch here. And what I do, I add a delay inside my tasklet to sort of to try and filter out these pulses here. And then we have to measure time. So I basically wait a couple of 100 milliseconds before I register the fact that this is a rising edge for my interrupt. On the RPi 4, there's no real time clock that comes with it, but the kernel in there uses a software clock, and it measures time in jiffies. And the size of a jiffy, it depends on a kernel constant called Hz or Hertz. You can see what the value of Hz is on your system. Just type getconf clock tick. On my system, it's 100 Hertz. So that means a jiffy is 0.01 seconds. All right, that's pretty much it. Any questions on that?
There's a couple questions in the chat.
Oh, okay.
There's a question: is there a GitHub repository with an example of the driver?
Sorry.
They're asking whether or not there's a GitHub repository.
Yeah, I'll put all that on. What I can do, I can. Is there a way of following up? And
yeah. Actually,
what I need to do, I'll create. I've got everything on a GitLab repository, and what I'll do, I'll create one for Raspberry Pi.
Yeah, you just reply in the chat. You can get the link, whatever.
Chat. Oh, okay.
Then William is asking for the same codings. There's also a question about how many times does kernel load the driver? Is it just once on boot time, or any time the driver is needed? So I guess.
So answer the first question about drivers. When I upload this, you normally upload this to the Facebook, don't we? Afterwards, the files. I'll put a page in the presentation with a link to the GitHub or GitLab repository. And drivers, they just get loaded once at boot time. Any experimental drivers you're doing yourself, you can load them when you want. You insert them. You might find you get some errors, in which case then you unload them and try and fix the error and then recompile it and load again.
So when you load it, then you reboot the machine. Is it still loaded, or do you have to load it again? Oh,
then you have to load it again. Yeah.
Okay. So how do you make it permanent in the?
Then, if you want it permanently in there, in that make file I mentioned. Yeah. So. Not sure if I can everyone see where my sort of cursor is?
Yeah.
So there's a line in there which says obj minus m equals hello.o. That is going to cause hello to be compiled as a kernel module, as a loadable kernel module, because of the m there, m for module. If you want to make that as a built-in module, you would have obj minus y there. Yes for built-in. Well, that will cause hello.o to become effectively part of the kernel image. And then you have to, the only problem with that is once you've done that, you've got to recompile the kernel image. and then boot up. So it's a bit of a longer process. But
you're a hardware supplier. Your hardware supplier, how do you do that? You're just saying on a hardware driver.
Normally, what you do with drivers is if it's hardware that's already on a platform, what the kernel in the driver you can register the driver with the kernel, so that when the kernel detects the hardware on your board, for example, it knows automatically to call the right driver and loads it. Yeah. So there's something we haven't really gone into yet here. But you can actually put code in your driver that registers it with the kernel in such a way that when the kernel detects a relevant piece of hardware being inserted, it'll automatically call that driver. So that happens already automatically for things like, for example, buses, USB buses, PCI buses, and so on. There's a whole core there for detecting hardware that's connected automatically, plugged in basically. And the kernel maintains a list of drivers that are relevant to a part. But, sorry, yeah.
Yeah, I've got a question. So when you're writing your code, you write the registers.
Yeah.
How do you know where they are in memory?
Yeah.
And are there any helper functions for writing to you in a tidy fashion?
Yeah, I thought that
straight in and write.
I thought that question would come up. Yeah. So this is the most difficult part actually of writing a driver with any piece of hardware. You have to get the data sheet for the hardware. So with the Raspberry Pi 4, all the GPIO registers are all part of the Broadcom chip, and there are actually data sheets for where those registers are and where they are in the memory, and you basically use those addresses to write to. Yeah.
So our Raspberry Pi, the GPIO pins are going to be always in the same place. They're not going to bounce around or load up in a different place.
Yeah.
In the same place.
I mean, if you want to I mean, what I did with my GPIO drivers, I actually used all those register addresses from the Broadcom data sheet, which is quite easy to download now. When the Raspberry Pi first came out, they were very secretive about it, but with the years they've got less secretive about it.
And you can then, when you know that address, you've understood how the hardware operates, you can just write straight to those.
Yeah, that's right. Yeah. They've got a fairly complex GPIO chip, which is in the address space of the ARM processor. So you go through the data sheet, you look where it is in the address space, and then you write that in your GPIO functions. What you find with Linux is they try and make driver writing for you each year a bit easier. So they already have a whole library. Instead of you having to get really low level into all these register addresses, there's a whole bunch of GPIO access functions. So there's like a GPIO core layer that Linux provides. So you can use that instead if you want to. Yeah. And they sort of have sort of fairly common bits of hardware that can be used for. Yeah. So that makes life a bit easier.
A few more questions in the chat.
Yeah.
We have to watch. Look at Anthony's questions. So removable hardware, you have to supply a way to load your.
Sorry, where is this?
In the chat, so you can move up.
How can we push driver from?
Yeah, you can ask that question as well.
Well, answer that one. Can we?
Yeah, just go ahead and read that one.
Okay, now. Oh, I see. How do we know where the registers are? Yeah. Can we see the code for that button into this now? A lot of code there. Anthony. If I give you my email address, I can send you the code. There's rather a lot of code there to
send a link
to
to
this.
GitLab, just in the chat. You do it after the question is done.
Yeah.
So I guess it's just one last question. I'm going to move on, but the last question there, that's a good one. How can we push driver from plugged-in device? We just set up some special files to point out the driver. So I don't know how that works.
Where was this? It says for removable hardware, do we have to load it? I may in response to some. I don't think so, because you rely on the driver to detect the to handle the IRQ. So you need a driver to actually to deal with the IRQ. I'm guessing, I've never done this, but I'm guessing what you might be able to do is to write a little stub driver that handles the IRQ and then sends a signal to user space. And then on that signal, you can perhaps load another driver in. But normally for removable hardware, it's there are, for example, USB hardware. There's a whole USB core layer in Linux. Maybe what's called a bus core. The bus detects, this bus core layer in Linux detects that a USB device has been plugged in. That causes the Linux kernel then to look up a list of drivers that might relate to that USB device. Usually USB devices have got ID numbers. From the ID number that the bus core is registered, it can then load the correct USB driver. That's typically what happens. You get that happening with PCR devices as well. Also, you get that with platform devices. So pieces of hardware that are already on your board, they have a thing what's called platform drivers, and that works along a sort of similar concept. So,
okay, we're going to move on.
Can a device drive? Yes, it can. That's yeah. This is where things get dangerous. Yeah. So the way read and write functions are done, something we haven't gone into here because we haven't got time. But there are special buffers set up for transferring data between user space and kernel space. So they're in effect decoupled from each other. So that anything horrible that's in user space can't get into kernel space. So there are some special transfer functions that, because again, what may be happening at any time, a user program is running and there may be some paging going on in memory. And if a driver is trying to send some data to user space, it could hit a memory fault if it tries to send data directly to user space memory. So we don't do that. So there's these special sort of safety buffers, you could say. One in user space, one in kernel space. And then there's a special transfer mechanism between those two buffers. Try and keep everything really clean. But
thanks very much.
Okay.